Welcome back. In this video, I want to continue our mini survey on group equivariant graph neural networks, but now focusing on those of the regular group convolution kind. And I think I can be a bit briefer on this topic as the previous ones, because regular group convolutions have been covered in detail in lecture 1 and also lecture 2. But there is one particular class of equivariant graph neural networks, which I'm framing as non-linear regular group convolutions, which I'm really excited about. So that's going to be the core focus of this lecture. It's actually focusing on the DimeNet slash GemNet type methods. So we're going to continue our analysis in terms of linear versus non-linear convolutions. So in lecture 1 and 2 and 3, actually, most of the time we've been looking at regular group convolutions, or group convolutions either of the regular type or the steerable type, right? And then we saw that when we move to this message passing framework, we can resort to very non-linear message functions, where the convolutions are a special case, which are linear message functions, which brings us to this idea of non-linear convolutions or non-linear equivariant operators. Okay, so we were going over this table, and I made a breakdown in these regular and steerable graph neural network type methods. We were focusing on this QM9, so this data set for predicting properties of small molecules. And really this benchmark was selected to have at least a nice set of papers that are somewhat representative of what's being done currently in this field of group equivariant graph neural networks. And now we will focus on the regular group convolution kinds. So we have SCHNET, which was already covered. So this point conv type group convolution, or actually just a planar convolution or an archery convolution, but with isotropic convolution kernels. And now we're going to take a look at this first paper on group convolutional neural networks for point clouds. So it's a specific type of graph neural network. So this one really quite literally extends the regular group convolution viewpoint to point clouds. So yeah, so I think it's good that we take a look at this paper as a starting point. So the paper is titled Generalizing Convolutional Neural Networks for Equivariance to Lie groups on Arbitrary Continuous Data. And Lie groups, that's a type of groups that have this continuous structure to them, and it's a very general class of groups. And I like this paper because they do not only focus on molecular point cloud data, but also on physical systems, or like problems coming from the physics domain, but also on what we know and have seen so many times in these lectures on images. Okay, I said we covered group convolutions already, so I can be kind of brief on this. So it covers the basic theory, also a bit on theory on Lie groups. But then the essence of this paper is in this group convolution operator, right? So this is really the group convolutions as we have seen it. So it's a slightly different notation. So U is a group element coming from our group, a set of elements in the group. So we want to sample the output of a convolution response on such a transformation, which means we have to transform a convolution kernel and then integrate it with the underlying signal. And before we wrote something like U1 applied to V, so a transformation via the inverse action of the group acting on the kernel, and then integrate it over F. So here we now see actually this order is changed. So V1 applied to U instead of U1 applied to V, but this is because here they talk about convolutions, and before we have been looking at correlations actually. Okay, so again, this group convolution can be thought of as a form of template matching with the kernel that is transformed and matched under the underlying against the underlying signal. And now the main change in this paper compared to what we've covered so far in regular group convolutions is that now we're working with point clouds. And so then we resort to point convolutions with here the appropriate references, and it also means we need a continuous parameterization of the convolution kernels. And that is what's being done in this paper via multi-layer perceptrons. And once you do that, then you can also exploit some efficiency tricks as explained in the papers below. All right, so now I won't go into much detail regarding this paper, apart from mentioning that indeed these kernels are parameterized via multi-layer perceptrons, And we call that multi-layer perceptrons take as input vectors and spit out new vectors, or matrices in this case. So these multi-layer perceptrons now act as neural fields that take as input coordinates and spit out transformation matrices. So that's a very convenient way of parameterizing your convolution kernel. And our remark made here is that here they exploit the Lie group structure to turn any group element, or let's say relative transformation, into a vector representation. So they use a particular type of coordinates that we can construct when dealing with Lie groups. So that makes sure that the inputs are not just group elements that can come from some manifold, but they are actually treated as vectors and therefore highly suitable for working with multi-layer perceptrons. So that's the logarithmic or the Lie group part of things, but everything else is just group convolutions on point clouds. And in this regular group convolution framework, we work actually with point clouds on the groups instead of on our base space or homogeneous space. For example, it could be that the input is maybe R2, like a 2D image, and the group is SE2, as to obtain convolutional neural networks that are equivalent to both the rotor translations. And that means we have to extend the domain with another axis that codes for all these subgroup rotations. So that's explained in this section, and also in the appendix they provide some clever tricks to keep everything computationally tractable. Now there's actually another nice contribution of this paper, and that is that they handle feature maps on some homogeneous space, or some space which is not necessarily a homogeneous space of the group itself. Meaning that if our input lives on the 2D plane and we want to have rotation equivariance, then certainly not every point can be reached with one rotation, right? So all these points, they transform via orbits independently from one another. And that requires then the need to split your domain in all these independent orbits and work with identifiers for each of these orbits. And that's nicely explained in this section. Suppose my input feature map lives on a d-dimensional Euclidean space, and I want to be equivalent to rotations. Then this embed gives you an identifier, okay, to which orbit belongs this particular point. And a unique identifier for each orbit is, of course, the radius of this ring. Each ring has its own radius, and each point with the same radius belongs to this same orbit. So this is gives you an identifier to which orbit a point belongs to. And a similar thing if you work in the Euclidean plane and you want to be equivalent to scalings, then each point is scaled along this ray going from the origin, right? I have a point, and if I scale it, I multiply it with that factor, it ends up in a different location, and so on. And so all these points live in independent rays, and these would be the direction vectors, would be the unique identifiers of these orbits. And I think this approach is unique that I haven't seen before in literature, and it basically tells us that where initially, if you work with the group convolution framework on a homogeneous space, so every point can be seen, we have weight sharing over all these transformations in the group. Now this section proposes a way of also having weight sharing over all these. Sorry, this is actually not weight sharing over this orbit. This actually says that they can use different kernels for all these different orbits. So they let their convolution kernels now also depend on these orbit identifiers. All right, but sorry, that's again getting into much detail, but the nice thing is it's nicely explained in this paper, and they have this nice way of working with orbits and non-transitive actions. And then they apply it to this QM9 dataset, of course, show that indeed they improve via equivariance over some other baselines, but also they apply it to systems in physics, focusing on the governing equations behind these dynamics, so these Hamiltonian systems. And these Hamiltonian systems have some symmetries in them, following from the conservation of energy. And so these symmetries are then hard-coded in these neural networks by just picking the appropriate set of symmetries that you want to be equivariant to. And so that's the nice thing about this Lie group formulation, is that we can nicely specify which group we want to be equivariant to, define the logarithmic map on the space, and then we can go ahead and do our computations. So they experimented with this and show that if we choose the appropriate set of symmetries, then the method generalizes with great precision. Okay, that's all I want to say about LeConf for now. It is a regular group convolution, just like SNET is. However, SNET was acting on R3, so that means we had to impose some kernel constraints. But if we lift the data to the group itself, then there are no constraints, and we talk about regular group convolutions, which are still, in this point cloud setting, we can think of them as convolutional graph neural network, as a message passage with linear operators, with linear message functions. So this is a linear group convolution type method. But we also saw that, just like in the previous lecture, that these methods can be adapted to become more nonlinear when we incorporate this kind of transformer type attention mechanisms in them. And that is what's being done in this paper, Lie transformer equivariant self-attention for Lie groups. Now, I don't want to give a breakdown of this paper. I just want to mention that this paper nicely covers the theory behind group convolutions on homogeneous spaces. So it is concise, and it's I think a great source to get a bit more intuition on the topic. And then it talks about Lie transformer and Lie groups. So again, here we have data on a homogeneous space which is lifted to the group by attaching to each point this fiber, or considering all subgroup transformation, which could be discretized with a finite set of elements. Okay, and then I just saw this nice sentence, like, we may design G equivariant maps on the space of functions on G, so on this lifted space, which is a simpler task than designing G equivariant maps directly on X. And I like this statement, and that's also how I felt for a long time. If we talk about group convolutions, it's often easier to talk about regular group convolutions, because that's just extending the convolutional viewpoint that we had before, template matching, but not just over translations, but over the group. But if we want to stick to these planar fields, then we have to talk about steerable feature vectors attached to each point. And that was the topic of lecture 2. So that is theory-wise a bit more involved. And so the authors of this paper also felt the same. Okay, let's stay focused. This is, again, a regular group convolution, but augmented with an attention mechanism. And this idea, if you want to learn more about attentive group convolutions and how to preserve equivariance while making the networks a bit more adaptive via attention mechanisms, I think these two papers by David Romero are also nice references. All right, but these methods are still almost linear. Okay, they made nonlinear via these attention components. But now I want to move on to methods which are extremely nonlinear. They're still equivariant, and hence I would like to call them nonlinear group convolutions, and they are of the regular kind because they don't work with steerable features. And one really seminal paper in this direction is called this directional message passing for molecular graphs. And I'm going to show that this can be thought of as a regular group convolution on the homogeneous space of 3D positions and their orientations, so directions, possibly with a scale factor that tells us something about the distance between points or atoms. So this R3 S2 is acted upon by rotations and translations in 3D. So we're here looking at DimeNet, and we're also going to take a quick look at its subsequent work, GemNet, which is an improvement over DimeNet by the same authors. Okay, so this is the paper. There's two important aspects to it. One, it provides an equivariant message passing framework, and secondly, it is super nonlinear in its aggregation step. And maybe that's the first thing to show. This is what their message passing neural network looks like. And obviously, you cannot make sense out of this figure by just quickly looking at it. I just want to mention that these interaction layers are of message passing type. So we have message function and aggregation steps. And in all these message and interaction steps, all these operations take place, right? So we have all these linear transformations, but we also see this bilinear product over here. So recall from one of the previous lectures that we can think of this as a conditional linear layer. And it's actually nice to see that this conditional linear layer, if you trace back this arrow, is linked to, let's say, some coordinate embedding. A coordinate embedding, which is additionally transformed via a linear transformation and then used as a conditioning factor in this bilinear layer. So what we're already seeing here is that we construct messages or transformations of messages that are conditioned by these geometric attributes, which we're going to take a look at quite soon. Then we also have these pointwise nonlinearities, which can also be thought of as conditional linear layers, like a restricted form of this tensor product. And yeah, so there's a lot of going on. So this, I think we can all agree that these message functions or these interaction layers are highly nonlinear. Then the next thing is to discuss, okay, what is equivariant about these architectures? And before I go in detail there, I want to mention that it's equivariant because all these messages are conditioned based on invariants, quantities that they could extract from the data, such as angles between edges and distances between atoms. And when we talk about angles, these are not vectors that we can just simply add, right? If I have a ring and I add, so like the direction 0 and 2 pi are close together, right? So if I add 2 pi to 0, I get something which is completely different in this factorial setting, right? They differ by an amount of 2 pi, where actually they are the same. So we have this periodicity in our parameterization there. So if we work with geometric quantities which are not vectors, we can vectorize them via basis functions. And we want to vectorize them because multilayer perceptrons like to work with vectors. So that's being done in this section, like angles are converted to spherical harmonics, such that we have a vectorized representation of this geometric quantity. And the same for distances, like a distance is a scalar. We could vectorize it into a vector of values that represents the coefficients of these basis functions. So this is all about vectorizing the geometric quantities, which we can use to condition the message functions on. So in the end, we end up with conditional linear layers. Let's say this is the feature that we want to transform, and this conditional linear layer is conditioned on a geometric quantity expanded in a particular basis, a set of basis functions. And we saw before that this then can be thought of as a convolution type message function. Okay, and this convolutional viewpoint or group convolutional viewpoint is actually being explicitly discussed in their follow-up work called GEMNet, like a universal directional graph neural network for molecules. So this paper, in addition to having great results on several benchmarks, is that they also provide a universality proof of their framework. So that part consists of showing that instead of working with the full steerable framework, which can be thought of as assigning to each point in your graph a function on the full group SO3, right, via these steerable features. And then show, well, the interaction layers take place via this Clebsch-Gordon tensor product, as discussed in the previous lecture. But in this paper, they make a point of saying that we do not need these steerable features. We can work with functions on S2 instead of SO3 per point. So instead of per point, we have all these steerable functions which encode for functions on SO3. They say, okay, we could also assign to each point a function on the sphere S2. Okay, so that's what they propose. Instead of working with intermediate SO3 representation, they switch to the spherical representation. So they already have previous work showed universality results for this general equivariant message passing framework. Here they show that also in the spherical case we have universality results, meaning that, summarized maybe over here, these two theorems together show that we can approximate any rotationally equivariant function using only representations on the sphere, where these functions really should be thought of as graph neural networks in this general sense that map some atomic point cloud, for example, to a prediction. And basically this type of neural networks proposed in this paper can represent any of such functions. And basically also here they have this nice expression: this results puts theory back in line with practice, where the best results are currently achieved without relying on these more expensive representations. So basically saying all this complicated steerable convolution theory with this Clebsch-Gordon tensor product, that's maybe overly complicated and expensive, and we could also stick to the more simple, let's say regular group convolution type framework. Now in this paper they not explicitly go over this regular group convolution setting. That's what I'm going to do for you in this slide, which I'm going to discuss in a minute. The roadmap towards this is actually slightly different than what they do in this paper, but I want to mention here that this represents the feature response. Let's say at each node, atom node A, I have a function over all directions. So I have a function on S2. And this response is in some way obtained via this equation. So this is like a pointwise interaction. And this is actually what you can think of as a group convolution with a function that only has values in particular directions. So yeah, this is looking a bit dense. So what I'm going to do, I'm going to go back to the slide and then link it back to what they derive here in the end. So we come to the same conclusion, saying that our update functions, or these convolution type operators, can be obtained with a filter that only depends on the distance between points and a certain type of angles. And so the F's are convolution filters and the H are the hidden representation at neighboring atoms B, and I's are the discrete orientations attached to each point in space. So the idea is the following, right? Suppose we have an atomic point cloud and a connectivity. And this connectivity can be represented by directed edges, right? So in the message passing framework, we have a message sent from this node to this node, but also from this node to that node, and so on. So we have all these directions of edges. And this actually in turn defines an edge cloud. So where initially we have points which have a particular location in space, now we have edges which have some base location, so a point in R3 and a direction pointing in the direction of its neighbor. So that's a direction in S2. And we could possibly augment this with a radius component, because we also for each edge have the length of this edge, right? But let's focus on the position orientation aspect of things. Then, so we see that this graph defines a grid of direction. So at this point, I have this orientation. Sorry, let's use a different color. At this point, we have this orientation, we have this orientation, and we have this orientation. So we already, like the graph itself defines a grid for us, and that's what they called an equivariant mesh in this paper. In the regular group convolution framework so far, we said if you have such a point, then we just sample for all possible rotations and index the response of rotated convolution kernels for all these directions. But this obviously needs you to, well, sample the results on a lot of different orientations. So we work with grids. And this was not so nice, so that led us to this idea of steerable group convolutions, where we actually index continuous functions or place continuous functions on the group at each point in space. Now, instead of doing this via spherical harmonics, they in this paper do not focus on, well, sampling all possible orientation, but only at those locations where we actually have data. So only the directions defined by the graph. Okay, so that's already telling us that we're not looking at steerable group convolutions, which code for all possible rotations or directions, but we're going to look at regular group convolutions where we're going to sample convolutional results only in a particular subset of directions. And we can do this because this mesh or this grid of directions is obtained in an equivariant way. If this point cloud rotates, these directions rotate accordingly. Okay, and then the idea is that we just have a point cloud of orientations and features attached to each location and direction. And then we're going to send messages between such local orientations. So I have a neighboring direction, which could have the same base point, but a different orientation. So I send messages between different orientations, but also with different spatial locations. So all these neighbors, so we have to define a connectivity in this lifted space, but all these neighbors, they send messages to each other. So that looks something like this. We send messages between edges, you can say. Okay, so we do message passing on the space of positions and orientations, and this is actually a homogeneous space of SE3, so we can talk about group convolutions. And the idea is as follows. R3 S2 defines a homogeneous space of SE3 because we can define an action that allows us to connect every point in space with some reference location. So let's pick this as an origin, so our reference element in R3S2. So it's located at the origin pointing along the z-axis, and I can move this to any other position and orientation by translating and rotating this vector such that it is aligned with this x, n. And I'm here defining, the action of the inverse group element, because that's also what we're going to need in the group convolution. So basically it means we're going to rotor translate our base point, and we're also going to rotate our direction vector. So we rotate it such that it's aligned over here. And via this action we can reach any point in space by simply picking some group action that maps this reference vector to that particular point. And I say some group element because there's actually many. All these rotations around the z-axis leave this point intact. So I do not have one unique element or a group element that maps this vector to this vector. I have a whole subgroup of SO2 rotations that I can apply to this point. So rotations around the z-axis that all bring us to the same point in space. So this is going to give us some invariance constraint later on, as we will see. Okay, but we're now talking about linear operators on a homogeneous space, and these are group convolutions. So let's recall lecture 1.6 and 1.7. So lecture 1.6 and 1.7. Where any equivariant operator on homogeneous spaces can be written in such a form, right? So we want to create now a new feature map. So we want to know the feature value at a position x and a corresponding orientation n at some atom a. Then this is an integral transform with a transformed convolution kernel, and I integrate it over my underlying feature map. So this, you see this convolution kernel is rotor translated. The convolution kernel itself is a function on position orientation space. That's just transformed via some group action that maps towards this point. Okay, so we're talking about regular group convolutions here. So let's just fill in the group action. Okay, so we have a rotor translation of the base point. We have a rotation of this direction vector. So we have indeed this transformed convolution kernel and the underlying feature map. And this is integrated over your entire domain, right? So this is a template matching. And since now we're working with graphs, we do not have the full domain at our exposure, but only a point cloud of neighbors. So we're actually summing over all spatial neighbors, so over all neighboring points and their corresponding orientations. So recall at each point we had a grid of direction vectors. So that's this notation. My neighboring point has a bunch of reference directions. And finally, I'm going to rewrite it a little bit by saying I define xb minus xa, this displacement vector, in this notation. So it's given by x ba. So that's the same notation as they use in the GemNet paper. Okay, so linear equivariant message passing has this format. This is the message function, a linear transformation of f, where the linear transformation kernel depends on this quantity. So a rotor translated base point and a rotation of the direction vector. But we also know that now we're working with a quotient space. So we had all these subgroup rotations around the x-axis, which all map to the same point in space. That also means that our convolution kernel should be invariant to the action of rotations around the z-axis. So we have to deal with this equivariance constraint. And this essentially implies that we need to do conditioning of this kernel on invariant attributes. Right? So we have to make sure that this action applied to x keeps the kernel invariant. And these are some invariant quantities that you can use that are invariant to these rotations. And you might want to use maybe different type of, you can think of different type of invariants that I can extract from the x part and which I can extract from the n part. But this is closely linking it to the GemNet and DimeNet paper, where this can be thought of as the constraint kernel in polar coordinates. So you have a radial part and an angular part, and in 3D these polar coordinates have this radial part and two angles, but from these two angles I can only use let's say the distance that our direction vector makes with the z angle, or the angle that it makes with the z-axis. Right, so if I look at this figure over here, the invariant that I can take from x comma n is this distance and the angle that it makes with the z-axis. So let's call it alpha, so this alpha. And similarly, the invariant that I can take from this n vector is the angle that it makes with the z-axis, so let's call that beta. So we can condition our kernel on these two invariants, or three invariants: the distance of the point to the origin, the angle that it makes with the z-axis, and the angle that the direction makes compared to the z-axis. All right, so let's fill this in our equation over here. So we have a group convolution kernel that can only depend on these quantities. So we now evaluate the kernel on the rotated points and the rotated angle. So we fill it in and we get this, right? So a convolution kernel, a convolution operator now has to be of this form in order to ensure invariance to these subgroup rotations. And obviously the rotation of the length of a rotated vector stays invariant, right? So this simplifies, we can get rid of that part. So the kernel only depends on this displacement vector. And then regarding the dependencies on these angles, we can actually rewrite this to a slightly more convenient form. So this is saying the angle between the z-axis and this rotated displacement vector. We can rewrite it as follows. Note that the angle between two vectors can be obtained as the arc cosine of the inner product between these two vectors, right? And okay, this inner product with the transpose over here, we can swap the order. So we can put the rotation matrix to the right of this x, a transpose and the inverse cancel out. So actually we're taking here the inner product with our displacement vector x and the rotated z vector, z-axis. And we were actually using the notation that is Rna applied to Ez gives us the direction vector of Na. So that was the notation that we were using here actually. So Rna was any rotation matrix that maps the z-axis to this reference direction Na. Sorry for not being explicit about that before. But the point here then is that this angle actually boils down to computing the angle that our displacement vector makes with our direction vector Na that we currently want to evaluate. And similarly, this one is computing the angle that the direction vector Na of my current atom makes with the direction that my neighbor atom has. So the final expression boils down to this, where we can condition between the displacement between points, where this would be my neighbor and this would be my current position and orientation, the neighbor position and orientation. So the distance between the base points we can use the angle that this displacement vector makes compared to our current orientation. So that is basically telling us that we can make a distinction between information coming from the front of us or from the side of us, speaking in terms of spatial information. And we can condition our kernel on the angle that our current direction makes with the direction of my neighbor. So these are the kind of invariants that we can leverage. Okay, so what I just showed based on the principles that we have already learned so far, especially in lecture 1.7, where we want to find equivariant operators between feature maps on homogeneous spaces, that these are of group convolution type. And if we have indeed a quotient structure there, we need to impose some invariance constraint, and thus these linear message functions can only depend on invariance. And these are precisely the invariants that are also derived or given in this DimeNet and GemNet papers. So let's go back to their paper and see what it looks like in their paper. All right, so in this paper they indeed derived that the feature maps that at each base point, atom location A, they have a certain grid direction RO, so we use the N notation. So for each base point and each direction, the result of the filtering response is given by, well, the current feature value at that direction, maybe scaled with a scalar value, and this convolutional message aggregation over here, where the neighbor feature value, so in the slide I use a notation f, x, b, and b, so at the neighboring position and orientation. So here they consider the base point b and some grid direction ri, that this transformation is conditioned on, well, the distance between the base point, the angle that this displacement vector makes with the direction of the neighbor, and the angle that these two directions make at both my evaluation direction and my neighboring direction. And I think there might be a typo here. I think this should be RO, so the grid direction of the point that I'm currently evaluating. At least that's what we just derived. But maybe that's equivalent in some sense. I'm not fully sure, but I'm pretty sure that what I just showed on the slides is correct. So I assume this could be an output. This should be the output grid direction. But what you see over here, so they say, our message function is a convolution type with a filter that only depends on these three invariants. And they actually made it separable in this implementation. So the convolution kernel or filter only depends on the spatial part and on this angular part separately. Okay, and now I hope it now has become clear that these kind of methods can indeed be thought of as regular group convolutions via the derivation that we just showed. And they are very non-linear via this complicated message update scheme. So that's also their premise. So they start off with a regular group convolution viewpoint, though they're not quite explicit on the group convolution part, except for here maybe in the steerable aspect, but not in the regular group convolution part. And then they make it more non-linear by working with these complicated message functions. So they say these message functions, they can now depend on these invariants that we just derived. And they work with multilayer perceptrons, so they want to have some nice vector representation of these invariant quantities, so they embed it into basis functions. A radial basis function and two types of spherical basis functions. So this one is based on the spheric harmonics, but it's also depending on the radial aspect. And this one is based on two types of angles, dihedral angles. I won't go into detail there, but these are very nice physics-informed embedding functions of these invariant quantities that we can use. Okay, and via these coordinate embeddings, let's say they come to these message functions, where actually it's noteworthy here that they use the convention that they're not message passing between points on a homogeneous space, but they say that we're doing message passing between edges. So the core structures that they're updating are these features attached to pairs of atoms. Yeah, and they update these representations, or yeah, they actually mix the terminology with messages, but they update these representations attached to each edge via these kind of update steps. But this, as just shown, can be thought of as a convolutional transformation of feature vectors with base points in a position orientation space. Okay, and they do that via this scheme, which again requires some dedication to really understand what's happening here. But the essential part is that the feature vectors attached to atom pairs, so attached to the edges, and the feature vectors attached to the nodes are iteratively updated via these message passing blocks or interaction blocks, where these blocks or these message functions in turn are conditioned on these invariant quantities. And hence we can look at this as non-linear regular group convolutions. Yeah, okay, and then finally they apply this to several benchmarks and they get really impressive results with this. And by sticking to this regular viewpoint and only using let's say scalar values as opposed to what's being done in the steerable case, they can also make it a little bit more scalable, and all in all it's very efficient and powerful. Okay, so back to the slide. So we have seen regular group convolutions, really, which are based on linear message functions, so convolutional message function, and then we saw DimeNet, which is a very, very non-linear adaptation of regular group convolutions, or at least that's how I like to look at these papers. And then subsequently, there's this paper called spherical message passing, which is really related to this DimeNet class of methods, but which adopts a slightly more organized way, or let's say general viewpoint on this whole message passing framework. So that's this paper, Spherical Message Passing for 3D Graph Neural Networks by Liu and Wang. Where I said before, it's maybe a bit more organized, as they really categorize the type of messages as messages that are being sent among edges, or between vertices, or let's say graph level representations. So we can send messages from nodes to edges and from edges to nodes. So this is actually a type of simplicial graph neural network, but in which the messages are conditioned on these invariants, which is illustrated later on. For example, in this example, if we have pairs of nodes, or triplets of nodes, or even quadruplets of nodes, we can compute angles which are invariant to SE3 or E3 rotations. We can compute all these distances, which are all invariant quantities that can be leveraged in these message functions. Okay, yeah, so I think you get the idea. So we have message and edge functions, node functions, graph functions that can all be conditions on invariance. And the higher order we get, if you talk about messages between edges, the more invariance we can leverage, and therefore the more powerful and better generalizable networks can be built. So that's all discussed in this paper. And then by the time of publication, yeah, so they again compared on several benchmarks, and via this principled approach, they were able to outperform DimeNet, for example. But then, yeah, as just showed, there was this follow-up work called GemNet, which again improved upon both. And so things keep evolving, but I think the nice principle here is you can make very nonlinear graph neural networks which condition, in which the messages are conditioned on invariance. And that creates a powerful notion of nonlinear regular group convolutions. Yeah, and then finally I want to mention this EGNM paper, which I also have discussed already, which is kind of close to the Schnedt paper because it operates on this base space R3, so there should be some kernel constraints, meaning in this case that the messages between nodes can only be conditioned based on the distance between the nodes, and that's the essential part about EGNN. Where maybe let's have a quick look at this paper. So EN equivariant graph neural networks. It's of this message passing kind. So this is the Gilman message passing framework. So they propose the following: these message functions can only be conditioned on these invariant geometric quantities. So the distance between points. But as an additional, let's say, addition to this message passing framework, they do not only just update the node features via this message passing steps, but they also update the current positions of these points. So that actually means in the next step, this quantity will be slightly different, and that creates an extra, let's say, nonlinear mechanism to compute interesting features. And this idea of updating the positions also makes sense, of course, when you work with dynamic graphs or want to do, let's say, trajectory forecasting. Okay, but with that, I want to end this lecture and wrap up this discussion of literature. So where we really saw the distinction between regular and steerable group convolutions. Both are indeed of group convolution type, equivariant, and hence nice. But then we generally see the more nonlinear we make these methods, the better they perform. And we just saw the extreme case of DimeNet or GemNet, which can be really thought of as a very nonlinear regular group convolution. And it is running really the state of the art on several benchmarks. But we also saw in the previous lecture that nowadays we also have very good and scalable steerable methods. So I guess the debate is still ongoing whether or not we should stick to steerable or regular. I think generally the regular group convolution framework is slightly more accessible as an entry point, but I think with the steerable setting we can really do interesting stuff, especially when we want to predict equivariant quantities such as vectors or tensors in general.